At 13,000 feet above sea level, on the slopes of a Mexican volcano, scientists are operating a massive observatory to catch invisible bullets. These are highly energetic gamma rays traveling across space, powerful enough to damage human cells and disrupt biological functions. Fortunately, they don't reach the ground intact. When these intense rays hit Earth's atmosphere, they shatter. The impact breaks them apart, creating a sprawling shower of smaller, safer particles that rain down through the air. To catch these fragments, scientists use massive water tanks. Because these incoming particles are moving faster than the speed of light, can travel through water, their entry creates a distinct physical reaction, a sharp, eerie blue flash known as Cherenkov light. By recording these split-second blue flashes inside terrestrial water tanks, researchers can measure the energy and trajectory of the incoming particles. This provides the only forensic evidence available to detect violent events happening deep in space that stay hidden from traditional telescopes. Researchers took the data from those water tanks and traced the trajectories of the particles backward. The math pointed them straight to the dense, gas-shrouded region at the center of the Milky Way. But the calculations revealed a discrepancy. The energy levels of these original gamma rays are mathematically too high to be caused by the known supermassive black hole at our galactic center. To generate this much force, there has to be a Pevatron hiding out there. A Pevatron acts as a massive, natural particle accelerator, capable of speeding up matter to energies far beyond what we can achieve on Earth. This diagram shows the internal logic of the engine. It captures basic protons and whips them around until they reach near light speed. When that particle eventually crashes into a gas cloud or magnetic field, it suddenly loses its energy, releasing it as high-energy gamma rays. These detections prove our immediate galactic neighborhood contains hyper-violent engines of unimaginable scale. We are only now finding the high-energy exhaust from these hidden machines. To find the origin of these engines, astronomers look back 13.5 billion years. Using the James Webb Space Telescope's infrared instruments, they can detect light from the universe's earliest stars and galaxies. Almost immediately, the telescope spotted thousands of little red dots scattered across the early sky. These anomalies appeared much earlier than standard models of galaxy formation predicted. This chart shows the relationship between a celestial object's physical size and its brightness. Normal early galaxies cluster predictably, but the red dots sit as extreme outliers, packed so tightly they break the laws of physics. 2024 spectroscopic data ruled out existing alternatives. They're too faint for quasars and don't match baby galaxies in dark matter halos. The physical evidence gathered from the early cosmos contradicts our foundational models of how the universe formed. This discovery forces researchers to consider radical new structures for early celestial bodies. To resolve the broken physics, physicists have proposed a new type of object, the black hole star. The mechanics of this object involve a supermassive black hole core wrapped in a colossal envelope of cold hydrogen gas. This massive atmosphere mimics the appearance of a normal star's light, but on a much larger scale. Unlike the Sun, which is powered by nuclear fusion, this star is fueled entirely by the central black hole devouring matter. As the hole consumes the surrounding gas, it converts that mass into the energy we see. This structure creates a specific forensic signature. The thick, cold atmosphere muffles the intense radiation coming from the core, which is why it appears as a faint, red infrared dot to our telescopes, rather than a blinding quasar. These black hole stars served as primary incubators for the universe's first supermassive black holes. They provided an environment where gravity could concentrate mass far faster than standard galaxy models allowed. The discovery of these early objects suggests a potential link between the black hole stars of the ancient universe and the Pevatrons in our own galaxy. They likely represent two different stages of a single evolutionary timeline. In the early universe, these stars acted as turbocharged builders, rapidly accumulating mass and shaping the cosmos before shutting their thick envelopes of gas. The supermassive black holes left behind by those ancient stars are the same entities powering the violent particle accelerators we detect today. As the stars faded, the naked black holes remained as the central engines of modern galaxies. The gamma-ray shrapnel hitting our atmosphere represents the exhaust of these mature engines. surviving remnants of the objects that helped assemble the universe. This research into the objects within our universe has led to a hypothesis about the structure of the universe itself, black hole cosmology. At the center of every black hole is a singularity, a point where matter is crushed to infinite density. Here, the normal rules of time, space, and matter break down, mimicking the conditions of the Big Bang. This table compares the physical metrics of our observable universe with a theoretical universe-sized black hole. If you calculate the total mass, average density, and radius of our universe, the numbers are identical to the mathematical outputs of a black hole with the same mass. This mathematical alignment suggests that black holes are the physical architecture containing our reality. If this holds true, the monsters we are struggling to observe are not just distant objects. They are the structures that define